Alright, in this video we are going to introduce the concept of an H-bridge, and our motivation is controlling the direction of a DC motor. So we're going to represent that with the circuit symbol of an M with a circle around it. And if we send, we're not going to get into the physics of DC motors in this video, but pretty much if we send electrical current through it in one direction, we say it's going to rotate one way. And if we send electrical current through it in the other direction, it's going to rotate the other way. And if you remember, I said I'm not going to get into the physics, but a quick aside, if you remember physics and the right-hand rule, where if you have current flowing through a wire, and then you do the right-hand rule, point your thumb in the direction of the wire and curl your fingers and all that, then there's a magnetic field around the wire. So for a basic DC motor, you reverse the direction of that current, you reverse the direction of the magnetic field, and you reverse the way the motor spins. So you have, for example, a robot common Arduino project, and you want your robot to be able to drive in reverse and not just forward, then you need to be able to reverse the direction of current through the motor. And in the previous couple videos in this series, we talked about both BJTs and MOSFETs, so two different types of transistors, where we had this basic configuration where you tied one pin of the transistor to ground, you sent a low power control signal from a microcontroller into one pin of the transistor, and then you had some higher, I don't like it when I draw, I'm going to draw that over here because it gets mad when I draw towards that part of the screen. Transistor, you have some high power load that you're using to control current through with the transistor, and then you have some low power control signal that is coming from your Arduino. And the problem here is that doesn't let you reverse the direction of current through the load. Okay, you have your power supply up here, call that V+, that your load is connected to, and I can't flip this or have current flow through the load the other way, but if I want to be able to reverse the direction of my DC motor, I need to do that, and I can't do it with just a single transistor. But to demonstrate how I can reverse the direction of current through a motor, forget about the transistors completely for a second and just pretend we have a bunch of mechanical switches. So I'm going to build a circuit. It's going to take me a second to draw out with 4 mechanical switches. Oops. Sorry, really doesn't like when I draw it down there either, apparently. Okay, so pretend that one's tied to ground. I just got too close to the corner. 2 kind of branches of the circuit that are going to look like this. Each branch has 2 switches in series between power and ground, and then I'm going to connect the motor in between like this, and you can start to see why this circuit is called an H-bridge, because it looks like an H. Now, I am going to close diagonally opposite pairs of switches here. So first, I'm going to close this switch, leave this one open, so my power there, have my motor here, and then I'm going to leave this switch over here open, but I'm going to close this one. And you can see that I now have a closed path from power through the motor to ground through these 2 diagonally opposite switches. And you can probably see where this is going if I open those and then close the diagonally opposite pair, or sorry, the other pair of diagonally opposite switches. So now I have this one over here closed. This one down here is open. And look, I now have a path from power to ground going the other way. So I have reversed the direction of current through my motor. And I kind of have 3 different states here. Either my motor is off, current's flowing one way, and let's say if we kind of arbitrarily just say, oh, that makes the motor to flow or spin clockwise, and this way is counterclockwise, then just by controlling these 4 switches, I can turn my motor off and control its direction. So again, for something like controlling a robot, where you want your robot to be able to go forward and backward and stop, this gives me control of all 3 things. The problem in this case with these 4 mechanical switches is that you might have thought that I actually kind of have a 4th state here that I don't really want. If I close all of the switches on one side accidentally, then I'm just going to have no current through my motor, and I'm going to have a short circuit between power and ground. So I don't know if I draw that in here. That's bad, because I have a short circuit, so I don't want that. So I want to avoid this 4th combination, but either of these other 3 combinations is fine. Now, instead of using mechanical switches, you're not going to reach in and toggle mechanical switches to steer your robot. You could do this with transistors, either the BJTs or NPN BJTs or N-channel MOSFETs we saw in the previous couple videos. You could replace each of these 4 switches with a transistor that you can then control electronically. So if I just kind of, I don't know, draw that here in a different color, I'm going to make my diagram a little messy. If I imagine each of these as a transistor which has a control pin, again, either the gate of a MOSFET or the base of a BJT, where I now have either a control signal, again, either a voltage for the MOSFET, current for the BJT, controlling a larger current, it acts like an electronically controlled switch. So in either case, I could build my own H-bridge out of 4 discrete transistors, but in practice, you usually don't do that. What you do is buy an integrated circuit that has all of these transistors included in a single package, along with some additional parts like a flyback diode, which we covered a few videos ago, which is going to help protect the transistors and the rest of your circuit from inductive voltage spikes when you abruptly shut the motor off. So again, you could build all of this from scratch yourself with 4 transistors and different flyback diodes and everything. But usually, if you need to control a motor, you're going to buy a motor driver or integrated circuit. So we're going to talk about an example of that next. So as an example, we're going to talk about the L9110 datasheet. Sorry, H-bridge, when this information just comes from its datasheet. So if you go look at the datasheet, this thing comes in an integrated circuit IC package with a little half notch on one side so you know which way is up. And it has 8 pins, 4 on each side. And if you just look at the diagram, those are labeled 0A, VCC, VCC, sorry, OB, GND, IB, IA, and GND. And you say, okay, great, I don't know what some of those acronyms stand for. You also need to look in the datasheet for a table somewhere that explains what the different pins are. So if you find that in the datasheet, you'll see that VCC is power, GND, maybe unsurprisingly, is ground. And you'll note that there are 2 of each there, so even if that seems electrically redundant, that actually helps with heat dissipation. So again, these things are designed to control higher current loads. So there's a lot of current flowing through these. It's not an ideal component. There's some internal resistances to the chip. The chip itself is going to get hot. So having those currents split between 2 pins each instead of just 1 kind of helps spread that heat out a little more. I stands for your input. So there are 2 of these, A and B. Those are going to be your control signals coming from your microcontroller. And O is your output, A and B. And again, those are going to go to your motor. So the datasheet may also usually have kind of a common circuit diagram or schematic showing the external connections. So in this case, it might look something like this, where you have this little flag symbol for your microcontroller pins. Again, that's IA and IB. And then ground looking like this. Now, this is something that confuses some students the first time they see this datasheet. Way back in an earlier video somewhere in the series, I think I talked about different conventions for representing when wires connect or when they cross each other. So in this specific datasheet, they are using the convention that a dot means a connection, and crossing like this just means the wires cross. So there might be other datasheets or other diagrams where they'll kind of draw a little loop or bridge like that to indicate, okay, those 2 wires are not connected there. But I have seen students get confused and go, okay, well, this must mean we're connecting all of our input signals to ground, which would then kind of negate or make your microcontroller pins useless here because everything would just be tied to ground. So don't do that. These wires are not connected here. This datasheet is using this convention where things are only connected if you have a dot. And then similarly on the other side, we're going to have output A and output B connected to your motor like this, and then VCC pins are both going to be connected to your external supply voltage, where again, this implies a crossing here, not a connection between these wires. So you're not just connecting one of your outputs directly to VCC, or then again, you're just kind of shorting that to power all the time. You're not going to be able to control your motor. So be careful with that. Here are your external connections to the circuit, and then the datasheet will also have a table that tells you what the outputs are based on the input values. So for every possible input combination of input values, you're going to have resulting output values. And in this case, we have if input A is high and input B is low, then output A is high and output B is low. So setting an input high turns the corresponding output high. But remember that we're doing this with transistors. Our input is coming from a lower power control signal, and the output is drawing power from some higher source, so our VCC in this case. So it's not, you might look at this and go, okay, well, what's the point of having something where the output is just the same as the input? I didn't change anything. In terms of logic levels, high or low, this is the same, but it is powering the motor from this higher, which this could be 12 volts or something, depending, you need to look up the maximum voltage rating for the H-bridge you're using. Whereas your microcontroller, which I haven't really drawn here, can be powered by something else. So the power for the motor is coming from this VCC and going through the H-bridge. It's not coming from the microcontroller pins. So continuing to go down that data table, if we switch the inputs to input A low, input B high, then output A is going to be low, output B is going to be high. So if we look at the first row of that data table, I'll do this in red over here. If output A is high and output B is low, then current's going to flow that way. And if I flip that, output B is high and output A is low, then current's going to flow the other way. So that's what's allowing me to reverse the direction of current through my motor. And then if I set both inputs low, then both outputs go low, and then the difference between the H-bridge and what we saw on the previous page, where I said, okay, if I turn on or close two switches on one side, then I'm going to have a short circuit to ground. The H-bridge has internal circuitry to prevent that. So if I set both my inputs high, then it's also just going to set both outputs low and turn the motor off. So the nice thing about the IC is you don't have to worry about this. Whereas if I was controlling this with 4 separate inputs, one for each switch, I would have to be very careful not to accidentally turn on the wrong pair of inputs. So you could look at this and say, okay, I could prevent that by only using 2 inputs. I could connect this input to that one and this input to that one, right? So if I only ever set one of these high at a time, then I could be sure that, okay, I'm never setting both of my inputs high and creating this short. But then in your code, if you did accidentally set both inputs high, you would still wind up creating this short, even if you reduced it to 2 inputs from 4. So the H-bridge kind of has additional internal circuitry to prevent that from happening. So you can set both of these inputs high or both of these inputs low, and you don't accidentally have to worry about shorting anything out. Now, this was just one example of a specific H-bridge. There are plenty of other ones, oops, wrong color, out there, so you need to look at the datasheet for the one you are using to figure out these pin connections in this table. For example, I still failed to change that to white. Let's try again. There we go. For example, another very popular one is the L293D, which has 16 pins instead of 8. I am not going to draw all of them out, but it allows you to do bidirectional control of 2 motors. And it also has 2 additional pins for dedicated speed control. So you could, we haven't really talked about this yet, but use something called a PWM signal to modulate the speed of a motor on these pins, where if you just send in 0 to one pin and then rather having the other pin high the entire time, you turn it on and off very rapidly. You can then use that to control the speed of the motor. On the L293D, it has 2 direction pins and then that you only set high or low, and then a 3rd pin intended for use with this PWM signal. So again, it's going to be specific to the H-bridge. These are just 2 popular ones that I have experience using. But the point is, you need to look up the datasheet for your H-bridge to find the pinout, the connection diagram, and then the table for what the outputs are going to be based on the state of the inputs. You also may need to look up information like the maximum voltage and current ratings for that external power supply and how those correspond to the ratings of your motor to make sure that the H-bridge is sized properly or can handle enough power. And all that is maybe a little more than we're going to go into in this video. Usually these popular H-bridges are fine when it comes to the small motors you would use with an Arduino for building a robot, because they can handle hundreds of milliamps or maybe up to an amp, and that's fine for those small motors. But when you're getting into larger motors, you have to start worrying more about heat dissipation and current limits and heat sinks and all that stuff. But again, not really going to go into that in this video series.